So here we are, Chapter 8, Basic Concept of Chemical Bonding. Make sure that you've got this page out in front of you so you can take notes, where it says the 4 pillars of bonding. Write down all these notes on here, and then we'll do some sample problems as we go along. Make sure that you've got these in front of you with a pen or a pencil. 4 pillars of bonding. There's 4 main types of bonding that we're going to study in chemistry class. The first one is called Ionic Bonding. The second one is called Covalent Bonding. The third type is called Metallic Bonding. And the fourth type is called Covalent Network, which is also sometimes known as AKA Coordinate Covalent Bonding. Those are the 4 pillars, those are the 4 types, and you need to be able to differentiate between those 4. So I'm going to give you what kinds of things stick together to make this kind of bond. And then we'll give you a couple of examples of each. And then we're going to go deep in depth into each type. In this chapter, when I say deep in depth, I really only mean one of these types. We'll spend about 2 minutes on that type, maybe 2 minutes on that type. We'll spend probably 1 video cast on ionic, and then we'll spend probably 4 video casts on covalent. So lots of time on covalent bonding in this chapter. So what types of things stick together to make this kind of bond? First of all, an ionic bond, it's a metal and a nonmetal, or a metal and a polyatomic ion, or 2 polyatomic ions. Now, if you forgot where the metals are on the periodic table, have a periodic table out near you. The metals are over here on the left-hand side of the periodic table. They're all of these guys up to where we've got this staircase right here. Remember, bordering the staircase, these guys are semimetals, so sometimes they can be involved in ionic bonding, sometimes not. Aluminum is a metal and is involved in ionic bonding almost all the time. So these guys are metals, and there has to be a metal almost all the time involved in ionic bonds, which really shortens things down because these are our only nonmetals along with hydrogen, nonmetals. And we're going to talk about covalent bonding in a little while, and those only involve nonmetals. So it can be pretty easy to tell apart because if it's got a metal in it, it's going to be an ionic bond. So those are the types of things that stick together to make an ionic bond. What makes ionic bonding unique is that there is a transfer of electrons. A transfer of electrons from one thing to another. A good example of this is potassium, who has 1 valence electron, we'll illustrate with a dot, and fluorine, who has 7 valence electrons, and we'll illustrate that with 7 dots. The electron from potassium is transferred to fluorine. Remember, potassium's a metal. Potassium's right over here on this side of the periodic table, okay? Fluorine, of course, is a nonmetal. It's right up here. And these two will transfer electrons to one another. This transfer of electrons occurs in ionic bonding. It's a completely unequal sharing of electrons and a completely sending of one electron, usually from the metal to the nonmetal, from the metal to the polyatomic ion, or from one polyatomic ion to another. A transfer of electrons. Keep that in mind for ionic bonds. Covalent bonds happen only between nonmetals, and as I illustrated before, the nonmetals are this upper right-hand corner of the periodic table along with hydrogen. These are the ones that make covalent bonds. Now, the semimetals are also involved in covalent bonding lots of times, but still that's a small amount of things on the periodic table that can be involved, but it makes millions and millions of different compounds, and it's all made of nonmetals. What makes covalent bonding unique is that there is a sharing of electrons, a sharing of electrons. The electrons are shared sometimes unequally, but the electrons are shared. For example, let's say that we had the element chlorine. Chlorine will illustrate its 7 valence electrons with 7 dots. And then we'll illustrate the other chlorine that it's going to share with 7 more dots. And these 2 electrons would be shared between these 2 chlorines, giving each 8 total valence electrons, which gives it what's called an octet of electrons, which all noble gases have, except for helium, who obeys the Duet Rule. Having 8 valence electrons is super important for these covalent things, as we'll see. Covalent occurs only between nonmetals, and there's a sharing of electrons. Sometimes an unequal sharing, and we'll talk about that during this chapter as we delve into detail about this unequal sharing. Third type is called metallic, and you can maybe guess what metallic bonds occur between. They occur between metals only. Like, for instance, what holds solid copper together? Well, it's called a metallic bond. And a metallic bond's knowing characteristic is what's called these unshared, or these electrons that are able to float around throughout the metal. Able to float around throughout the metal and not really be attached to anything. These metallic bonds have lots of free electrons. Free electrons that are able to float between one another. And these allow the metals to bond to several neighboring atoms, and the electrons are free to move throughout the 3-dimensional structure. These free electrons, free moving electrons, give rise to typical metallic properties such as high conductivity of electricity and of heat. And they have usually high what's called luster. Luster makes them very shiny. And these unshared or free electrons that can buzz throughout the solid give it these characteristics. Most metals, when they're by themselves, are held together by metallic bonds. And remember, metals are this whole area of the periodic table. So if you ever see a metal or an alloy of a metal, 2 metals stuck together, 2 or more, they're stuck together or held together by metallic bonds. The third and last, or fourth to last pillar of bonding are these things called covalent network. And these are unique. Covalent network bonds are unique in that they're between carbon and silicon, and sometimes involve oxygen. For example, carbon that's in the form of diamond is a covalent networkly bonded structure. This is strong bonds from carbons to carbons to carbons, and I'm drawing these dashes because these dashes illustrate that the carbons are stuck together to one another, and then they also stick together to other carbons, forming this strong lattice. This strong lattice that usually has a really high boiling point, a really high melting point, and it sticks them together super duper strong. Silicon dioxide is a good example of this. Silicon dioxide is known as sand in its covalent network state, and of course sand melts at a fairly high temperature and it sticks together really, really well. Other carbon structures also have a little bit of oxygen in them, but these are 2 examples where we have carbons sticking together and silicons sticking together. There are also millions and millions more of compounds that have carbon in them that are not stuck together with these covalent network. Just these special ones like solid carbon in the form of diamond or graphite are usually stuck together with these coordinate covalent type bonds. Well, like I said at the outset, these are the 4 pillars. We're not going to spend a ton of time on the 2 on the right hand side. Metallic bonding and covalent network bonding are the two that we're not going to spend a ton of time on at all, but we'll touch on them right now, and then we'll come back to them again in chapter 11 next year just a little bit. But it's important that you can differentiate between these pillars of bonding, because you've got to be able to tell the difference between coordinate covalent metallic bonds and regular covalent and regular ionic. Metallic bonds, once again, are characterized by just metals, and they can be a single or more than one metal stuck together, and they're characterized by these delocalized electrons, and the delocalized electrons give it its characteristic property of malleability, ductility, and make them good conductors of heat and electricity, and they usually have good luster. Malleability means that you can hammer them into shapes when you heat them up. Ductility means you can draw them into wires. Good conductor means that it's a good conductor of heat or electricity because of these delocalized electrons, and that they have luster. They're shiny because these electrons reflect the light. And then you can see lots of shininess at the top of them. That's about all we're going to talk about. Just know that there's lots of unshared electrons that float throughout the metallically bonded things, and it occurs between metals. Well, between metal and metals. Covalent network bonding. Covalent network are networks of atoms that are connected by really special, strong covalent bonds. Special, strong covalent bonds. And examples of this are diamond, quartz, which is a form of silicon dioxide. Silicon dioxide, which is another kind of name for sand, as well as another example. They're very hard. They often have really high melting points. Really high melting points. They're poor thermal and electrical conductivities. That means they don't conduct heat very well. So that makes them pretty good insulators. As far as electricity goes, they don't conduct very well. And they're stuck together by these really strong covalent bonds that need to break to make them melt or eventually change from one phase to the other. That's about all the time we're going to spend in this chapter on those two pillars of bonding. We'll come back to both in chapter 11, but you need to be able to recognize that, hey, metallic bonds are stuck together by metals. Covalent network are things like diamond and quartz that involve carbon or involve silicon dioxide. And that's what makes those two special. Now I'm going to move on to section 8.1 and 8.2 and focus in on the third pillar of bonding known as ionic bonding. Ionic bonding, remember, are bonds that occur between a metal and a nonmetal, a metal and a polyatomic ion, or two polyatomic ions. A metal and a nonmetal, a metal and a polyatomic ion, or in rare cases, two polyatomic ions. Notice that almost all of these have to have a metal stuck together with something that contains nonmetals. Polyatomic ions always contain a nonmetal. So, what does a ionic bond actually look like? You can think of an ionic bond as something that has an electron that is given away, or you could say stolen by something else. I used these symbolisms a little bit earlier to illustrate this. These symbols with dots, like for instance sulfur that's in group 16 of the periodic table and would have 6 valence electrons. I put 6 dots around it, 1, 2, 3, 4, 5, and 6 to illustrate that. These symbols are called Lewis electron dot structures. And these illustrate the valence electrons. Remember the S and P electrons from the highest energy level for any metal or non-metal. If, for example, let's say sulfur encountered a metal called magnesium. Magnesium, if you look at it on the periodic table, is over here on the left-hand side. It has 2 valence electrons because it's in group 2. And we could draw magnesium as having 2 valence electrons here. It's commonly drawn that 2 electrons are on each side of a symbol, but you can put them anywhere. It doesn't really matter. These 2 electrons would be transferred or given away or stolen by sulfur. And then these 2 electrons would give sulfur an octet of electrons, and magnesium would then become an Mg positive 2 ion because it would have lost 2 electrons. Remember the joke? The joke about losing an electrons? You know, 2 atoms are walking down the street. Here's one atom, here's another atom, and this atom says, I think I've lost an electron. And this electron says, are you sure? Are you sure? Are you sure you have? Sure, this is the word sure. And this one says, yes, I'm positive. Ha ha ha, get it? Positive, you know, positive. And what happened to magnesium? He lost 2 negative things, and so he became positive 2 charged. So that's, you know, the joke of the day about the 2 atoms walking down the street losing an electrons, and yes, I'm positive. The electron being given away is what ionic bonding is. And these electrons that are given away actually have a rating scale or an energy associated with them. And the energy associated with energy, this is an N right here, with ionic bonds is called lattice energy. And lattice energy actually has an equation. Lattice energy is defined as a constant K times Q1 times Q2 divided by D, where Q1 and Q2 are the charges on the 2 ions that are sticking together, and D is the distance between the 2 ions. K is a constant, and the constant that it actually has to do with something called Coulomb's law, and it's like 9 times 10 to the 9th joules times meters per Coulomb squared, which is on page 306 of 10th edition of the textbook, but it's not really necessary to know. The thing that you have to recognize here is the relationship. You have to see that the lattice energy, which holds these 2 metal and non-metal things together, is directly proportional to the charge. And don't take into account that one's positive and one's negative. Just look at the magnitude, the value of the charged things. In this case, magnesium is positive 2 and sulfur is negative 2 because it gained 2 electrons. And so the numbers would be 2 and 2 up here. And the distance between them is the distance, the bonding distance, and can be determined by their ionic radius. Which you learned last chapter. And you can look at the trend on the periodic table, and if you remember, the radius of something on the periodic table increases as you go down, and radius also increases as you go to the left on the periodic table. So things over here are bigger than things over here, if you forgot what the trend for atomic radius is. And so you can see that the distance between 2 things is inversely proportional to the lattice energy. What does inversely proportional mean? If the distance is greater, the lattice energy is smaller. If the distance is smaller, the lattice energy is larger. So it's an opposite relationship. Let's take a look at an example of how you can use lattice energy to determine how well 2 things will ionically stick together. Take, for example, NaI, and then take, for example, our other one, MgS. who has the greater lattice energy and therefore would have the greater temperature needed to melt these two salts? Well, you can tell they're both ionically bonded because they both have a metal and a nonmetal stuck together. And if you look at the lattice energy of these two, the lattice energy of NaI would be K times Q1 and Q2. Remember, ignore the negative on the iodine and ignore the positive on the sodium, divided by the distance of the two. And if you look on the periodic table, you can remember that sodium has a positive 1 charge. Iodine would have a negative 1 charge because it's in group 17. Now the lattice energy for MgS would be equal to K. Magnesium would be positive 2, and sulfur would be negative 2. But remember, ignore the positives and negatives for now and just look at the magnitude. Magnesium is positive 2 because it's in group 2. Sulfur is negative 2 because it's in group 16 right here, and everything in group 16 is negative 2, especially in an ionic bond. And then divide it by the distance. And if you just ignore the distances for now, because there's a little bit of difference, but it's not a huge difference, you can see that this is going to have a 4 on the top, and this is just going to have a 1. And therefore, this lattice energy is going to be way bigger and might have a much higher melting point, and therefore have a much stronger lattice energy. Now, you can take a look at some lattice energies in your textbook. As a matter of fact, on page 305 of your textbook, I'm just going to zoom in on this table. This gives you some examples of lattice energies of various substances. And you can see right here that something like LiF that has a very small atomic radius has a lattice energy of about 1,000 kilojoules per mole. But then if you look at something like we were studying before that has a +2 and a -2 charge, like MgO, that's like almost 3.7, almost 4 times as strong because it has a +2 and a -2 versus a +1 and a -1 charge. And you can see some differences here too between lithium fluoride and then, for example, something like cesium iodide. Just because both of them have a +1 and a -1 charge, you can also look at the distance between the two, and you can see that lithium and fluorine, lithium here and fluorine right here, are going to have a small distance between the two because their ionic radius is fairly small at the top of the periodic table, whereas something like cesium and iodine, which is way down here, cesium's way down here, it's going to have a much larger atomic radius. And you remember, a distance is inversely proportional to lattice energy, and so this is why this lattice energy is much, much smaller than this lattice energy right up here. Well, lattice energy is the strength that holds the bond together between these two items. And this strength that holds these two is actually measured by what's called an enthalpy. And remember from chapter 5, enthalpy is delta H. Enthalpy is symbolized as delta H. And this enthalpy is the lattice energy. There's usually a L-I-L-A-T-T-I-C below it. And this is the amount of energy it takes to break that bond. And to separate these two ions right here, for example, magnesium and sulfur, you would have to put energy in to the system to break the ionic bond. And that's at the top of your page already typed for you. You must put energy into the system to break the ionic bond. So, is it endo or exothermic? Well, it's an endothermic process that must be done to break this bond. And if you look at the lattice energies once again in your book, you can look at all of these numbers and they're all positive. It's because from the viewpoint of the system, which is these chemicals right here, you have to put energy into them to break them apart or separate those structures. All right. That kind of wraps up lattice energy and ionic bonding, and we're going to move on to the biggest pillar the biggest pillar of bonding, which is known as covalent bonding, at least biggest time-wise that we're going to spend on. Not saying that the most compounds are covalently bonded, but an awful lot are. We're going to spend a ton of time on covalent bonding in this chapter, and not to belittle the other ones, but ionic bonding, metallic bonding, and covalent network bonding are going to get a little bit ignored now for a while, for the next couple of video casts. Not that they're not important, we're still going to need to know what they are, and we're going to need to differentiate in a compound what the difference is between these three things. But we're going to focus on covalent bonding because there's a lot we know about it, and there's a lot of things you need to know about it to be successful at it. Covalent bonding is a sharing of electrons. And to determine how much electrons are shared, we have a rating scale. And the rating scale that we use to determine how covalent and how much sharing substances are is called the Electronegativity scale. The electronegativity scale is a rating scale on the periodic table that tells us how much an atom wants an electron. It's actually kind of related to the periodic trend that we learned in Chapter 7 that was called Electron Affinity. In Electron Affinity, we looked at an energy that was released when something gained an electron, or energy that had to be put in to force something to gain an electron. But this electronegativity scale takes away those units, and we just rank things on the periodic table as to which things want electrons the most. And if you look on page 312 in your textbook, this is the 10th edition. Now, in case you have a different edition, you'll have to find it on a different page. You can see right here the rating scale in a really nice diagram. And you can see the things that have the most electronegativity and therefore attract electrons the most are in the upper right-hand corner, where fluorine right here is the Tyrannosaurus rex of the elements and wants electrons the most and attracts them the most. Then we've got chlorine, nitrogen, and oxygen as the kind of like the big three right up here on the top as far as electronegativity goes. Chlorine's pretty close fourth. And then you can see some of these yellow elements in here. They've got pretty strong electronegativities compared to some of these purple ones over here, but not nearly as strong as these big three up here. And so the trend for electronegativity goes from fluorine, kitty corner, down here to cesium. The most electronegatives up here, the least electronegative is down here. And this periodic trend needs to be memorized, and you need to understand why this periodic trend occurs. And you got to know which things are the most electronegative and which things are the least. You can see that mostly, for the most part, metals are the least electronegative, and these are the most. And this comes back to knowing something called the Octet Rule. And the Octet Rule says that all atoms on the periodic table eventually would like to fill their valence shell with 8 electrons. Now, we'll find some exceptions to this, but for the most part, almost everything wants to have 8 if it can. And that's why ionic bonding occurs too, because something can end up having 8 electrons by stripping some electrons away from someone else. In covalent bonding, sharing occurs to complete an octet for two or more atoms in a particular structure. Now, depending on the electronegativity rating of the 2 or more things that are coming together, there is a sharing that is equal or unequal, depending on how well the electrons are shared between the 2 nonmetals. Covalent bonding, if I didn't say this before, only occurs between nonmetals. Only occurs between 2 or more nonmetals. And so you can always tell in some of these covalently bonding, just because, bang, it's only got nonmetals in it. It'll never have that metallic or ionic bonding that occurs. Well, Watch video 3 for how to illustrate covalently bonded molecules using Lewis electron dot structures. But before you get to that video 3, I just wanted to show you a couple more things about this sharing that's equal or unequal using electronegativity values on the periodic table. Let's say, for example, that we have the element hydrogen, which has one valence electron because it's in group 1 on the periodic table right up here. And hydrogen, remember, is a nonmetal even though it's stuck over here with the metals. And the element fluorine, the Tyrannosaurus rex of elements, that has 7 valence electrons around it. Well, if we look, fluorine is in group 17 and therefore it has 7 valence electrons. And hydrogen and fluorine combo together, so fluorine can have 8 valence electrons. Fluorine ends up borrowing hydrogen's electron, and a hydrogen ends up borrowing the electron from fluorine. And so we have some sharing going on, and immediately we see a problem. I just barked a little while about how everything wants to follow the octet rule, and immediately we see an exception. One of the exceptions, and one of the biggest exceptions, is hydrogen. Hydrogen is the biggest breaker of the octet rule because hydrogen only has a 1s orbital of electrons. A 1s orbital can only have 2 electrons in it, and this 1s2 electron structure would give it a noble gas configuration that's very, very stable. As a matter of fact, it would look like the element helium. And therefore, hydrogen has its own rule. Its rule is called the Duet Rule. And the Duet Rule means that it only wants 2 electrons ever. Hydrogen never breaks this rule. It only wants 2 electrons and will stick together with something so it can share electrons. And therefore, you'll never see hydrogen bonded multiply with something else. It will only have one bond coming off of it. This hydrogen fluorine then that forms is an H, and I'll put a dash here to illustrate that there are 2 electrons being shared to this F. That's actually an unequal sharing of the electrons. If you remember from the book, fluorine, being the Tyrannosaurus rex of the elements, has the highest electronegativity. Hydrogen, on the other hand, has a decent electronegativity, but nothing like fluorine. And so fluorine has an unequal sharing of electrons and pulls the electrons towards itself. And so we can draw an arrow like this, indicating there is something, get ready now, I'm going to use a fancy science term, called a dipole moment that is constructed between hydrogen and fluorine, where there's more of a buildup of negative charge over here by the fluorine because it pulled hydrogen's electron close to itself, and there's more of a positive charge buildup over here on the hydrogen because hydrogen is now lacking its electron, and therefore its nucleus, which contains a proton that's positive, is very exposed. We can also illustrate this dipole moment with this small Greek letter delta. The small Greek letter delta looks kind of like an S, and we put a little negative sign here indicating that there's a partial negative charge on this side of the molecule, and we can put a small Greek letter delta with a little positive sign on this side indicating that there's more of a positive charge on this side of the molecule. You see this unequal sharing in many, many molecules, and this unequal sharing causes this bond right here to have a fancy name. It's called a dipole moment, or for short, scientists call this a polar bond. Not because it has anything to do with white bears, polar bears, not because it has anything to do with polar bears, but because it has 2 poles, a positive pole and a negative pole. The positive and the negative poles give it a dipole. What does the prefix di mean? 2 poles, a positive and a negative. So you've got to learn these fancy names and this fancy terminology for this stuff. When there's an unequal sharing of electrons, we have what's called a polar bond, which means that there's an unequal sharing of electrons because one element is more electronegative than the other. And electronegativity, remember, is a rating scale that tells you how much something wants an electron versus something else. And since fluorine is the most electronegative atom on the periodic table, it sets up a dipole moment. You can actually see in your textbook on page 313, if you have this version of the text, where they show hydrogen fluoride right here in a colorful document or a colorful picture, where this is hydrogen with a blue all around it and fluorine over here with a red. Red means there's a great amount of electron density, and hydrogen right here is lacking electrons, and you can see that it's very, very unequal sharing. You can see here in lithium fluoride, it's just as bad, where there's lots and lots of electrons over here next to the fluorine, and little to none over here around the lithium, exposing its nucleus. These are computer-generated renderings showing the calculated electron density distribution on the surface of the fluorine, which would be what's called a non-polar bonded structure. Notice how there's just total equal sharing here. They're both the same size, and there isn't like a blue area in one area. The hydrogen fluoride molecule right here and the lithium fluoride molecule. The regions of relatively low electron density appear blue here and here, and those with really relatively high electron density appear in red. The regions that are close to electrically neutral appear green, and that's why this molecule is entirely green, is because the electrons are shared very, very evenly. This idea of electronegativity and bond polarity, this idea of electronegativity and bond polarity is critical to your understanding of how things stick together. Well, I already introduced dipole moments here a little while ago. Your book actually goes into a way to calculate the dipole moment. We won't be doing that, but you need to be able to know that there's a difference in charge in electronegativity between these two things, and that's what makes these things have the bond strength that they do due to this unequal sharing of electrons. In our next video cast, on the next few pages of your packet, watch video 3 to figure out how to illustrate these covalently bonded molecules using Lewis electron dot structures. Good luck with your ionic, covalent, metallic, and covalent network bonding.